Hi, my name is Jimmy Chen. I'm a research scientist with Google Quantum AI, and it's my pleasure today to talk to you about our work on quantum error correction with the Sycamore devices. So this work was just published in Nature last week, and I encourage you to follow the QR code to read and learn more about it. So as we heard from the hardware leads this morning, our next milestone is to demonstrate the fundamentals of quantum error correction. Specifically, we want to show that if we increase the size of a logical qubit, or in quantum error correction parlance, the code distance, that we'll get a decrease in logical error rates with our preferred architecture, the surface code. Now, we're actually working on this in the lab today, but what I want to tell you about today is an experiment that we've done to really give us confidence that this might work. And that's our work with repetition code. So a repetition code is a 1D version of the surface code, where the surface code has the sort of checkerboard pattern. With the repetition codes, we have a 1D chain of qubits, where we alternate between data qubits, which store the data that we're trying to preserve, and measure qubits, which try to detect errors in the data qubits. Now, by going from 2D to 1D, we lose the ability to correct for both types of quantum errors, phase flip and bit flip. When we set these repetition codes up, we basically have to set them up in one mode or the other. However, 1D does give us an advantage, which is that we can scale these repetition codes to much larger code distances with less qubits than the surface code. In particular, we'll be able to test something, the exponential reduction of logical error rates with code distance. This is something that's been promised to us by quantum error correction, and that's the data that we'll be really after today. So let me give you a little demonstration of how the repetition code works with a 5-qubit example here, where we have 3 data qubits and 2 measure qubits that are interleaved. So we start by initializing the data qubits into a state that we know about. We then run this little circuit here that's called a stabilizer circuit. And what it does is it maps the parity of the data qubits, of 2 of the data qubits, onto one of the measure qubits. And then we read the state of the measure qubit out. We do the stabilizer circuit many times over many rounds. And then finally, at the end, we measure the final state of the data qubits, apply some corrections, and compare it to what we initialized. So how does the circuit actually detect errors that occur on our data qubits? Well, let's look at an example of running this stabilizer circuit for 2 rounds. So in the first round, let's say that no errors have occurred, and we're going to read the state 0 out of both our measure qubits because we've initialized our data qubits into even parity states. In the second round, we're going to have an error on the middle qubit here, and that's actually going to flip the parity of both pairs of qubits, and we're going to get the state 1 on both the measure qubits. So what we see is that an error on the data qubits causes a change in the parity measurements of our measure qubits, and we call these changes detection events. They signal that an error has occurred somewhere in the device. Now, the important thing is that the pattern of detection events that we get depends on the location of the errors. For example, if I have an error on the bottom data qubit, I'm only going to flip the bottom measure qubit. And so conversely, we can also use the pattern of detection events to try to back out what the errors are that might have occurred. We call this process decoding, and it's how we try to figure out what corrections to apply to our data qubits. Now, as we've heard, this scheme only works if our component operations, the control Z and the measurement, have very low error rates, because otherwise we're introducing more errors than we can correct. So here I'm showing the cumulative distribution of the error rates of the component operations in our repetition code, the Hadamard gates, the control Z entangling gates, and the measurements. Importantly, we benchmark these while we're operating all the operations simultaneously, just like we do in the repetition code. And simultaneous operation is really important because it sort of saves the amount of time that we need to do these error correction cycles. And as we've seen before on the Sycamore devices, we can still achieve high fidelity while operating our operations in parallel. Now, just having these high fidelity operations was sort of the first step to getting this experiment to work. We've had to learn a lot of other new things in order to get quantum error correction to work successfully. One example of that is reset. So we're applying these reset gates after every one of our measurements on the measure qubits. And traditionally, you can think of reset as turning the 1 state into the 0 state. But importantly for us, the reset also turns the 2 state of the trans 1 qubit also into 0. Now, 2 states can arise from error processes associated with both the control Z gates as well as the measurements. And if left to their own devices, these 2 states can potentially poison multiple rounds of quantum error correction because they can have fairly long lifetimes. So on the right here, I'm showing a plot from Matt McCune's paper where we show the mean 2-state population of both the data and measure qubits as a function of the number of rounds that we've run of quantum error correction. we see that when we introduce these reset gates, we get a significant decrease in the amount of leakage that we get. And this turns out to be really important for the stability of our error correction codes. Another thing we learned is that a potential huge source of error is that when we're doing the measurements on our measure qubits, there's actually some crosstalk into the measurement resonators of the data qubits. And this is a really big source of phase decoherence on the data qubits because, in effect, we're sort of accidentally measuring the data qubits when we don't need to do so. But some nice work by my colleague Sabrina Hong showed that we can actually completely mitigate this effect by adding decoupling pulses on the data qubits. And this turns out to be really important when we're operating the repetition code in phase flip mode. Okay, so now let's put all these ingredients together and look at how our repetition code performs. So the most basic metric we can look at is something called the detection event fraction. That's the fraction of parity measurements that we see that actually signal that an error has occurred. So what we see is that about 10% of all our parity measurements signal an error detection. And importantly, the detection event fraction is constant versus the number of rounds. And this is really important because it indicates that our repetition code is stable. Errors are not sort of building up over time. And we attribute this stability to the introduction of these reset gates. Now, detection event fractions are sort of the most basic way of looking at our data. We've also been developing new analysis techniques for quantum error correction. So my colleague Juan Atalaya developed this technique to look at actually the correlations between pairs of detection events. Using these correlations, we can make these cool matrix plots, which reveal error mechanisms like crosstalk, which we previously hadn't been able to explore. At the end of the day, what we care about is the logical error performance of our codes. So let me just quickly walk you through how we determine that. So we've initialized our data qubits into a certain state, and we're collecting all these parity measurements from our measure qubits. Some of these parity measurements signal a detection event. We go through the process of decoding, where we use a technique called matching, which you can think of as literally connecting the dots between our detection events. Decoding tells us what corrections to apply, and in this particular case example that I have here, the corrected final state of the data qubits equals the initial state, which means that we've successfully preserved this information in the data qubits. However, sometimes this process will fail. Perhaps there are too many errors for us to decode unambiguously into the errors that actually happened. In that case, the corrected final state will not equal the initial state, and we've incurred a logical error. So here on the plot, I'm showing the probability of getting logical error as a function of both the number of rounds of error correction that we've run, as well as the number of qubits, ranging from 5 to 21. And what we see is a dramatic decrease in the logical error probability as a function of the number of qubits. We can try to quantify this more by fitting each one of these curves and getting the logical error per round of error correction. So here I'm showing the logical error per round as a function of number of qubits on a semi-log plot. We see a 2-order magnitude decrease in the logical error rate. And we also see a straight line in semi-log space, which means that we're really getting this exponential error suppression, as promised to us by quantum error correction theory. So this is a really exciting result. This is the first time we've ever observed exponential error suppression in a system where we're doing these repetitive stabilizer measurements. And while the repetition code is not as complicated as the surface code, it contains all the same ingredients and is a really good first hardware integration test for the Sycamore device running error correction. Additionally, this experiment was also a really good test for our theoretical models. So some work by my colleague Cody Jones showed that simulations of our experiment with simple error models reproduce the experimental values reasonably well. These same error models also point to the fact that we're going to need improvements to hit our surface code milestone. We need about a 50% decrease in the total component error rates. Nonetheless, we have run surface codes on the Sycamore device. In the same work, we showed that a distance 2 surface code, which is the smallest surface code that you can run, works on the Sycamore device. And some work by my colleague Kevin Satzinger shows that the results agree reasonably well with, again, numerical simulations. So to summarize, we can run the repetition code on the Sycamore device with high fidelity component operations. When we run the repetition code, we suppress our logical errors exponentially with the code size, which is what was promised to us by quantum error correction theory. And the path forward is to continue to run larger surface codes and continuously improve our component error rates. Thank you for listening to my talk, and up next will be Matt McEwen telling us about cosmic rays.